Welcome everybody. It's a great pleasure for me to moderate today the webinar about photonics for steel manufacturing and processing. My name is Francesca Moglia. I am the laser expert in EPIC, and I'm really looking forward to really motivate and animate some new synergies between two initiatives that are dealing with the steel manufacturing and processing, and namely are MULTIPLE and LAMpAS. And it's let's say it's the program is really easy. We will have to now. This is the agenda. We will start with a couple of words from myself about EPIC first, then a couple of words about the projects themselves, but then we will dive into the two experiences that we have with MULTIPLE and LAMpAS. So we will have two speakers, Pavel, so Ignacio Fachado first from LDL, as our end user in MULTIPLE. Then we will have Pavel Kluczynski from Eroptic as also supporter of this use case in MULTIPLE. Then we will move to LAMpAS, and we will talk about all the monitoring systems mostly. So that's why we want to bring the connection to the MULTIPLE, to the LAMpAS. You will hear later why. And we will have Nikolai Schröder first, and then Rodrigo Linares. We will conclude then with some closing words, but also some networking. So if you are interested to talk to our speakers and also to ask more questions, you are very welcome to stay online and also have a chit chat offline. So we will then be not anymore visible to everybody. So now, just to give a couple of words about EPIC. So EPIC is easy, this slide. It's them. It's also the little logos you see behind me. So we are the largest photonics industry association in the world, and these are all the members that we have at the moment, and it's really growing fast. As you see here, bottom right, we have above 700 members. And basically, what is the idea behind EPIC is to promote the sustainable development of the organization that are working in photonics on the world level, but of course, with a pain and attention, a little eye on Europe. And also, we are supporting the technology and commercial advancement of this technology and these companies. So for you that are listening, probably it's trivial to know and to understand what is photonics. There are really a lot of topics in this, so including lasers, optics, imaging systems, sensors, photonics integrated circuits, all in the possible applications of industrial, medical, research, defense, everything that you see here, and probably we forgot some, are those that are covering the full photonics world. Then basically the little heads on the bottom is the team. So we are 13 at the moment, and we are all taking care of all these members, and that the photonics really is improving and getting more successful and more visibility also among other technologies. So that's why here I reported a bit of our activity. We publish market and technology reports. We organize technology workshop and B2B roundtables to really bring together possible and potential partners for future collaborations to really foster activities together, not only in the photonics world, but also with system integrators and end users. Then we have a lot of initiatives. Also, we coordinate EU funding proposals. We are lobbying for more also financement from the European Commission towards photonics, and all these activities that are also present on our website. So you are very free to join us and see what is really EPIC doing for the photonics community. And then it's time maybe now to spend a couple of words about the two initiatives that we have here today, MULTIPLE and LAMpAS. So I start with MULTIPLE, that represents the future of photonics-based process optimization. This is basically what we are now planning to offer. We are halfway of our project, and the idea is to really provide cost-effective multimodal monitoring solutions. We have a full solution that will be really monitoring and optimizing the manufacturing chains in different industrial fields. And then we have 5 building blocks products that basically can be flexibly combined to each other and also used for different applications. For example, we have snapshot, visible and sphere hyperspectral imaging cameras, laser-based IR analyzers that we will hear our partner today about it, organic electronics-based spectrometers, multimodal monitoring systems, and cloud and edge computing platform and services. So this is the 3 areas that we are actually now facing as use cases in the project. It's clear that today, considering the topic, we will focus on steel manufacturing, and for woodworking and food industry, you're of course very welcome to join us and check our website and also connecting to us. And these are the other partners, including those that are here today. And so we will hear more about the focus on steel processing in a bit. First, I have to spend 2 other words about LAMpAS. So LAMpAS is there for basically giving us the possibility of surface enhancement inspired by nature. Because basically we realize that if you inspiring by nature, so you can see that if we can control topographic characteristics over surfaces, we can really give special functionalities to surfaces. And this can be antibacterial, self-cleaning properties, friction reduction, optical security function, or even decorative effects. And this is possible usually with coatings or with extra chemical components that we can add to surfaces, but also with lasers. And this is possible only with special lasers, so with the ultra short pulse lasers actually, that can really generate these multi-scale topographies on the surfaces that play the game of giving these characteristics to the surfaces. The problem is, this is possible, yes, in research labs, but is really not yet suitable for mass production and low cost, and especially high throughput. So that is what now LAMpAS is trying to do with these basically 6 pillars of activities. So as I said, we need a high power ultra short pulse laser, but what is actually the key role is interference patterning. That is what we are applying with our ultra fast laser, and also fast polygon scanners. But nothing of this would happen without the monitoring control. And so that's why today we will focus a bit more on how to monitor in processes, so that we have the link with multiple. Now you are starting to build the puzzle pieces together, I assume, and then we will integrate everything in a device, so in a big machine, a system design from our partner Lasea, and then we will be able to use it also for different applications. But for this, maybe we will talk about it in another webinar soon. We focus today more on process control. These are the partners that are working with us, together with the two that are in the room today. This is also the way to reach us, but please keep in mind, you can also reach myself. You see my email address there for any questions we'll have also after this. We can basically reach me, and I will redirect you and inform you about what is useful for you and what MULTIPLE or LAMpAS can do for you. So now, I don't steal more time to our speakers. We start with Ignazio Fasciado from LDL, and I guess I stop share my screen so that you can share yours, because the floor now, Ignazio, is yours. You are muted. That's the standard. No, you are still muted.
Now.
Yes, now, sorry. Very well. No problem.
Good afternoon, everybody. I will introduce our LAMpAS company, okay? LAMpAS let me here. Sorry, I cannot find now.
With the space bar, you can change.
Now, yeah. Okay.
Yeah, yeah. Perfect.
Okay. Sorry about that. LAMpAS LDL key data. We are the latest European rolling mill. It's a greenfield project in Tarnos, France. We start operations in first quarter of 2018 with the production of heavy plates. We have a capacity of about 500,000 tons. We have 20,000 square meters in a 10 hectares. Okay, we are based in Tarnos. Is a small town based at the port of Bayonne in France, in the Bay of Biscay. Okay. What we do, LAMpAS manufactures heavy plates of reliable tested quality. Our target is to offer the highest quality steel, thermomechanically controlled, raw fine grain steels, high tensile heat treated, fine grain steels, and wear resistant steels. We need to make the difference, or we try to make the difference going to the highest quality. So the market is focused on normalized fine grain steels, obviously certified to the higher European standard, ASTM, ASME, etc. We are now also producing steel for on and offshore structure, the wind farms. We start now doing also place for shipbuilding, and in the future we will be able to make place grip resistant steel for pressure vessels. Okay. The project was based in two of our main services of the plant, in the furnace and the rolling cage. You see we are in the plant, our furnace and the rolling cage. Our furnace is a pusher type reheating furnace with a capacity of 80 tons per hour, working in 3 rows of slabs with a maximum length bit more of 3 meters each. Is complete of a slab charging device, again pusher type, and the sharing system with independent trolleys. We can put slabs of a thickness between 2 and 300 millimeters wide, from 1850 to 2500 and about 30 tons maximum weight. The rolling temperature that this furnace has to reach the slab is 1200 degrees. Okay. We roll in a quarter type rolling mill. So we have 4 rolls, two backup rolls and 2 wheel rolls. The back rolls, they are 1600 millimeters diameter, and the wheel rolls 950. The big ones weighs about 63 tons, and the wheel rolls 23 tons. We have 2 electric motors giving 6,000 horsepower and producing a separate 4,000 tons. We have all control and the thickness adjusting system by hydraulic screw downs with automatic control. Okay, which AHC. So what is the steel place secret? Is the combination of forces, temperature, and time. Okay, the objective is to reach quality plus N and plus M. That means plus N is we call normalized roll. Is the process which the final deformation is carried out within a specific temperature range. The result is equivalent to normalization through heat treatment in furnace. In this case, the rolling temperature is always above the transformation temperature. And we have also the objective to produce plus M, is called thermomechanical rolling. That means that the final deformation is carried out within a special temperature range in order to achieve a steel with a special characteristic that they are not possible to obtain with a simple heat treatment. The result is very high quality steel, fine grain microstructure with simultaneously offer good strength and cold forming properties. This can also be combined with a process with increased cooling speed as accelerate cooling process. Okay. So now we are entering now in the multiple process. Okay, what we have done in the furnace, we have implemented isotopic gas analyzers. These gas analyzers will allow us to control the gas from areas within the oven. We have 5 areas, and we are allowed to much better control the working of the furnace. We will reduce the delays due low temperature. Sometimes when we start the rolling in the beginning of the the ship, despite the system tell us that we have the temperature, we start the first slab and we see when start rolling that it didn't reach the proper temperature. So that will allow to reduce these delays at the beginning of the shift. This gas analyzer will also allow to secure the regulation of the furnace, secure the combustion, and reducing the CO2 and NOx. Okay. Another benefit that we will be able to control the temperature, and then we can secure that the plate is getting the right properties. Okay, so that will allow us to better improve the quality. We will reduce the gas consumption, so that's important for us because average we can spend about 200,000 euros per month in gas, so it's important for us. And this will allow also to reduce as consequence of all the earlier inputs, we will reduce the production of the slag, so that the slag is still that we will not be able to sell as a plate, so it's a loss. So the less slag we make, the better will be. Okay. And finally, in the rolling cage, we have installed 3D cameras at the entry of and the exit of the rolling cage that will allow to us to better control the thickness and also the steel grade. So this way we will avoid that some slabs are loaded by mistake, and is another checking point that will help. So the benefit of these cameras will be that we will have more reliability when controlling the temperature. Nowadays we have some temposonic, but it's always about how to calibrate the temposonic. Always checking. We have to check very often if the temposonic work properly or not. So with this way, with the cameras, that will have to see if the temposonic are right or not. Okay. We have also installed thermometer after the level. Again, will help us to control. I mean, to measure the thickness of the plate. I mean, whenever we have to calculate from the slab to the plate, the programmation is always focused on to match the norm tolerances, but also with the objective to use less slab as possible. So, but it might happen that the calculations are wrong and we don't reach to the thickness tolerance. So the more we control it, the better it will be for us. And also another benefit of this perfilometer that will allow to automatize the process, because nowadays we are controlling the thickness by hand. We will abide this hand control, and we allow also to better control the grade of the plates. So basically it's all about the process, and we are very confident that now we are in the process to activate all the data collecting, and we expect to reach the target. Okay. So for me, it's okay. If you have any question, you know where we are. We can talk a bit later. Okay. Thank you very much for your attention.
Thank you very much, Ignacio. Thanks a
Thank
lot.
So,
yes, so thanks a lot for this introduction to your company and also what MULTIPLE is doing for you. Maybe I know already here in the room there are some people interested also on the camera side of the devices that we are implementing for you. For the gas sensing, we will hear Pavel right after you, so maybe we don't go into details there, but maybe consider, Ignacio, that I wanted to bring you closer to the epic world and to the epic events. I will ask you now a question that is the so-called epic question. That is what can you do for them and what can they do for you? In this case, of course, you presented already what LDL is doing, but maybe you can give us another couple of hints on how photonics could help you. That is a part of this, of course, devices that you discussed already. Is there something in other also stages of the manufacturing that you think that you are interested to talk with the photonics companies? Anything that comes to your mind?
Basically, I will say again, just for us, we see big potential for both the machine itself and then the process and the final product. So it's a combination. So the more control we have on the way the furnace is working, that will benefits in the process and in the final product quality. So it's a combination of also.
Okay, so also a bit of automation. Also, it could improve also the use of some processes. That's very interesting. Yeah. So the idea is that we want always, so Epic is really interested in knowing what the potential end user are interested in for photonic side. So definitely we have to keep you in mind and to engage with you more because that is what really is important for us to understand also what you don't think yet it is possible, but maybe it's already possible. And, and working with you, it just helps. And so, yeah, so if there are no further questions, we 3, 2, 1. I don't see anything further, so we can move on to the second speaker that will explain a bit more the part of the laser-based gas sensing. So it's a big pleasure to have today Pavel Kluczynski from Aeroptic. And so now, Pavel, the floor is yours.
Okay, hello everybody. I hope you can hear me.
Yes, we can hear you and we see perfectly.
Thank you very much, Francesca. So, so my name is Pavel Kluczynski. I'm the CEO of Aeroptic, and today I will talk about application of laser-based analyzers in steel industry. So I will try to maybe present more from the actually analyzer side rather than application, because you already presented what is the goal for usage of the gas analyzers. So first of all, some brief information about our company. So we are a small medium enterprise based in Poznań, in Poland. And we manufacture laser-based gas analyzers for various industrial applications. So steel industry is something which we actually started very recently. But we mainly focus on applications in industries where traditional gas measurement is difficult because, say, of high temperature or difficult conditions, or where, for example, the fast response times is very necessary, as well as low maintenance. And so we mainly work with power industry, petrochemical industry, chemical industry, wood industry, and as I mentioned, also steel. We have in-house technology and R&D department on site, so we can also make a customized solutions for customers if there is a special request. We mainly work on as export. 90% of total revenues accounts for export and 10% for internal market. And so we have different kinds of gas analyzers. They're all based on laser technology. Today I will only talk about so-called in situ analyzers, so the ones which are used basically directly on the process, so without any sample conditioning. But just to mention, we have also open path analyzers, so we use laser technology to measure around the fence, so we can measure, say, the leakages from different industries on the up to 1 kilometer distance. And finally, the extractive analyzers, more like traditional type, where the sample is extracted from the, say, pipeline with some sample conditioning system, and then the analysis is done internally in the analyzer. It's more like gas chromatograph, but it's based on laser technology. But it's a bit outside of the scope, so let me continue. So if it comes to the in situ analyzers, as I mentioned, the systems are relatively easy mounted on the process. It can be a chimney, it can be a furnace, it can be any pipeline. And then you do it with different kind of flanges. So in Europe, we have DN50 flanges, but we have also ANSI standards, say for American market, and also GIS for Asian, and that's basically just a matter of configuration. But the idea is that you measure directly in the process, so you have a very fast response time to whatever happens to the flue gas or the gas you measure, and that's why we can have different applications for control. So basically, process control of different industrial processes. Typically, combustion control. It can be also safety application, like you basically monitor some process and monitor some gas which is critical to the process, like carbon monoxide and oxygen. The oldest application was actually SCR, so selective catalytic reduction, so the denitrification process in the power plant. But there are many different applications, yes. So that's and in the steel industry also try to use our systems already. And now what we do in multiple is more very, say, advanced type of application you want to obtain. So the principle of operation, the physics is very simple. So this is based on the absorption technology. The system consists of two units. It's a transmitter unit which sends the light from one side of the process to the other, so shining the light exactly through the process. And then what we do is we measure the absorption of the gas. So the gas acts like a filter, basically, which selectively reduces the light intensity after passing through the process. So that's in principle very simple physics, but the difficulty in practical conditions are that normally you don't only have the gas of interest, you have also a lot of dust. For example, if you burn coal in the coal-fired power plant, there's a lot of dust which scatters light more than actually the molecules absorb. So but the analyzer is capable of distinguishing between one and the other. So it's very selective and very sensitive. So absorbances down to 10 to -7 in relative units. So compared to FTIR, this is already three orders of magnitude. So one of the typical example of the application is combustion control. So in the beginning, we only use the oxygen system. So we are measuring oxygen basically directly in the boiler above the fireplace to try to optimize the combustion process in real time by using our signal. Then we also added carbon monoxide analyzers, so you can actually try to optimize combustion a little bit closer. And that's what's typically used in the boilers, so not in the steel plants, but say it's a bit lower temperatures, say in the power plants or in some chemical processes, and anywhere you have a combustion. And it seems to be already well-proven technology and accepted. So the drawback of the in-situ lasers are that they are basically very selective, but you need basically one analyzer for one gas. So what we did in 2018, we released a model which combines two lasers into one analyzer. So the form factor is basically the same, but you are measuring both carbon monoxide and oxygen and water in one analyzer. And this has already been proven in, say, smaller stacks and for combustion optimization in smaller boilers, I'm sorry, and also in some power plants. And then what we try to do is we ask ourselves the question, can we use it also for different processes like steel industry? And that's what we did also a couple of years back, but for a little bit simpler case when we had a hot rolling mill and optimize the furnace conditions by either measuring the oxygen or carbon monoxide or both. And the only difference with the boiler was that here the temperatures were up to 1350 degrees. but so the conditions were slightly more difficult, but it's also proved that this technology can be applied to the steel industry. And there are some technical issues here that we have to add some additional cooling devices if the ambient temperature is above plus 55 degrees, but nevertheless, it proved to be working fine. So the next step was so that, except for combustion control, can we use something else? Can we use some other type of optimization? So what we did is also we had the installation for the optimizing of the fuel, also the measurement of the fuel composition of the gas which feeds the furnaces. And that was done also, for example, in the case when the gas used for the reheating furnace is mixing different type of gases available in the plant. And these components can be changing in time. So the customer wanted to have the knowledge of the real-time composition of the gases. And we deployed two analyzers, one measuring methane, ethylene, and water vapor, and the other carbon monoxide, CO2, and H2S. So basically, this was enough for customer to indicate some additional knowledge in real time about the gas feeding the furnace. And now, finally, what we try to do in multiple projects, so together with LDL and Ursula and Ayman, is to have a very advanced analysis of what's going on in the reheating furnace. So as Ignacio already showed, there is a plan to deploy analyzers in 3 different points, as well as not only measure the carbon monoxide and oxygen, but also extend it to temperature, water vapor, and CO2, and also NOx. It's not shown on the graph, but basically to have a very complex analysis in the real time of the gas composition. And by means of this, we hope to save the energy, basically by optimizing the combustion process really close and more precise, but also to reduce the waste in form of basically some waste material. That's what also Ignacio mentioned in his presentation, that if the combustion is not sufficient or in the conditions in the furnace are not optimal, then it produces waste. So that's already, the project has basically started recently. So now our systems are installed at the LDR. And I hope the first results can be expected, I think, in September already. And so we are all very curious how it will all work and in the closed loop system, because the idea is also to use our outputs of the gas concentration in the edge computing device. That's the whole idea about the multiple. And also I hope with combination with the camera information to have a more profound control of the furnace condition. So this is really something new which never had been tried before. So we are all very excited. But from our part, from the just analyzer part, we think that just to summarize, basically in situ technology as such can provide really fast response times, because this was already proven, and which in general can be used in the fast closed loop control, because basically most of our clients use our analyzer in the fast loop control. So this is really something really standard in the power plant today. And also the temperatures, there is basically no limit of the high temperature for the spectroscopy. And then basically because we use laser, it's very selective and sensitive. So it's not like the non-dispersive techniques. And last but not least, these analyzers are also made that we have 24/7 operation. They have a self-calibration feature, which basically gives you a low maintenance, low cost of ownership in the end. And mechanically, they're also, suitable for this type of environment. And we also have a possibility to deploy them in the hazardous areas if necessary, for example, for zone 1 or even zone 0. So basically, this concludes my talk, and I'll be happy to take any questions.
Thanks a lot, Pavel. Thanks a lot also for highlighting a bit, yeah, the specialty of multiple, and also especially your role, of course, in this. I have to say, the important thing that is multiple doing, a part of this adaptability to different situations, to different manufacturing conditions, is also the broad spectrum of that we are covering. So we can go from visible to mid-IR, and actually you are the mid-IR person in multiple. So for us in EPIC is really important because we are now started an adventure with the Mid-IR Alliance, and so it's basically an initiative to push a bit more the mid-IR technologies. And here in the room we have also Rodrigo that later will talk about this wavelength range. So today is also a bit the long wavelength meeting. So maybe Pavel, you can tell us a bit what is your experiences, because of course you are an integrator of mid-IR technology since you started, basically, because that's of course a range of high interest. And so you can maybe give us a hint on what are the challenges now also for you as integrator of these technologies that you think that could be faced to even improve, of course, for your technology for steel processing, but also who knows also for other application and in gas sensing anyway.
Yes, so definitely. So Francesca, of course, the paramount the goal is to be able to combine mid-infrared technology and with near-infrared technology. So basically to create a wide broadband coverage, because broadband coverage gives you a possibility to measure several components at the same time. This is something which everybody needs in any industry, because you know, we need more tight control. So it's, the more parameter you control, the more gases you measure in our case, and it's added value. So of course the challenge is to being able to combine, you know, the wide wavelength ranges with the available photonics, you know, the devices today.
Yeah, so that's very good for us to know, because the idea is if you have something specific, of course, this is something we want to work with you as well as for really direct bullet points where we can really improve this and get in an advanced situation to also for the mid-IR technology. So that's very good to know. Be aware that we are working on this, and we are always keen on improvements on this in this direction. So now we have two questions. So I would start first with Thierry from Lambda X. I don't know if you can speak up yourself. Maybe I guess you should be able to talk.
Yes, can you hear me?
Yeah, we can. So you wrote a question in the chat, but please feel free to ask yourself the question.
Okay, so yeah, I am. It seems that gas composition control and measurement is a technique of choice to control the process for steel manufacturing. But I was wondering, it's rather an indirect control. Maybe it's quite direct if you want to monitor your combustion gases and control your gas expenses. But for steel quality, we have worked at Lambda X on a technique which enables to make a direct measurement of the steel by optical emission spectroscopy. And I was wondering whether maybe for LDL, this technique would be interesting for them to monitor the composition of their steel, measuring elements by using this technique.
Yeah, Ignazio. That's a direct offer. What do you say? You are muted now? Wait a second. We unmute you. Yeah.
Yes. Good afternoon, Terry. Yeah, of course, we will be happy learning how it works your process, and because I said the more we control and do the preventive, the less waste and the less money we spend somewhere else. So no, we'll be happy learning more, so we can keep the dialogue next day whenever you want. Okay.
The only limitation is you might need you need to sample your steel for that, but which means you can take you need to take a small sample on the line, and then you get the results in some seconds, maximum 1 minute. So it's not it will not be a real-time measurement, but it will be direct. So I don't know if it is meaningful for your process to do that.
During the process, I see that difficult because we are working, start the rolling the slab at 1,200 degrees, and nowadays we don't know how to do it. Maybe
okay.
you will have the techniques to
no
the samples. So.
No,
we don't know. I'm afraid.
Okay. Yeah, thank you. Yes, no, we don't have any technique to extract piece part just to do this control of the material. But we have been involved in a development to do the optics part. I mean, to design a spectrometer that was able to extract the elements in the steel by optical means.
Yeah, but then you know the point. We have here two people now that would like to work together. You miss maybe one in between that can support you, and maybe EPIC can help you in this. So let's keep this opportunity in mind, and then offline we can also see if we can see a way to bring Thierry to LDL. Okay,
This
is my plan also on my on my shoulder. So now we have also another question from Frank. You have raised your hand. Please, you can feel free to speak. Frank, do you hear us? You have your raised hand, but I see you're still unmuted. I can give you another 3 seconds. Unfortunately, let me check if I can unmute you. Yeah, no. Yes, but I'm not strong enough. So in case you try later.
Okay, now it works.
Yes, now it works. Yes.
Yeah, okay, sorry. I was in a completely wrong window. I'm so used to Teams. So this is Frank van den Berg from Steel. Yeah, Pavel, thank you very much for your presentation. If I understood you well, the examples that you showed so far, they were really focused on measuring the gases which are supplied to the furnace. If we look at the reheating furnaces, but not yet really in situ. So we would really like to measure the composition, real time inside these reheating furnaces. And if I understood you well, this is planned for the future. Well, one of the issues there is, of course, that you will measure across a length of about 3 meters with the furnace or even more. So it's a sort of integration that you will do, integrated length, sort of average. Are there also means to, measure this, but then position resolved, so along the length of your beam? Because again, usually with the DOAS techniques and the optical absorption spectroscopy, you will measure only along the length, but I can imagine if you use, for example, pulse lasers and very high, time resolved signals, you can even do this, resolved over the length of your beam. What's your opinion on this?
Well, okay, so to maybe to answer the first part of the question, yeah. So yes, so the fuel measurements were done in situ actually in the pipeline, and we also already used the technology for the hot rolling mills. So they actually were much longer than 3 meters, and then. But you're right. That's what we are giving the customer is the integrated concentration over the path length, so the average, so to speak. But it has proven to be already better than the point measurements, and at least what we had received from the customer. Yes, but of course, if you would like to have more special resolution of the furnace, then of course you need to install more sensors in some more complex geometry. That's clear. But as long as you have a homogeneous distribution, then it's not necessary.
Yeah, but probably in practice with the burners, there is never a homogeneous situation in the furnace, I'm afraid. But yes, it's something to think about. Also, in a more fundamental perspective, I would say, in the development of the measurement technology.
Yes, that's exactly the idea. And of course, you know, if you look back in the past, you know, when the people were using only the, say, extractive type of probes, so basically you were sampling the gas from one point only, and it was already used for some sort of trials of closed-loop control. Then this integrated path lengths, assuming more or less laminar flow or homogeneous distribution, is already added value. But of course, ideally, I mean, it would be much better to have something which also gives you a spatial distribution, yes. But then we need more sensors.
Okay, thanks.
Good.
Perfect. Thank you, Frank. Thank you for this observation and questions for deeper in the technology that for sure Pavel will find interesting. So now I guess,
work, yeah.
Thanks a lot. So now it's time to a bit move on because the time is unfortunately running. But just to give you a bit of the overlap now. So what LAMPAS can do now is something actually that is, I was talking beforehand that about surface structuring and basically giving special characteristics to surfaces. This is done especially on metal at the moment. So that's why we want to see if maybe from the product of Inazio, we can already give some added value to these surfaces to sell it to then their customers. But this, to know a bit better about this, I'm really happy to give the floor now to Nikolai Schröder from the Technical University of Dresden that will introduce also a bit LAMPAS in general and also go deeper a bit on the monitoring system. So to see how we can help each other also back and forth. So you see,
Right.
multiple can help here, and LAMPAS can help there, and other way around. So the floor is yours, Nikolai.
Thank you very much, Francesca. It's great to be back here on stage. Let's share my screen. I hope everybody can see it and hear me pretty well.
You can go.
All right. So yeah, today I'm going to present you a new approach for monitoring a DLIP process, and of course, giving a short overview about the LAMPAS project. Yeah, my name is Nikolai Schröder. I'm a research associate at the Technical University of Dresden. And as we can see where is the laser pointer? As we can see in this map, Dresden is located in the eastern part of Germany with this beautiful old town and a lot of their faked rainbows in the sky. It is about a 2 hours ride away from Berlin. I'm also a member of the so-called CAMP team. CAMP stands for Center for Advanced Microphotonics, and it is a research collaboration between the Technical University of Dresden and the Fraunhofer IWS, which is also placed in Dresden. And what are we doing there? I can say we are doing everything concerning surface structuring by a laser, starting from the process, then going to the special designed application, and of course to the characterization of these surfaces. What is inspiring us? Let me say nature is inspiring us. On the left-hand side, we can see some examples of nature, a plant leaf, a butterfly, and a bug. I think everybody knows how they look like in real life. But when we take a closer look to the surface of these objects, we can see a pretty alien-like and far away from this world. Here, maybe when we can go to the plant, I think everybody knows the lotus effect. And this lotus effect is caused by the unique surface structure. In this case, it is pretty water repellent and self-cleaning. The butterfly has no color directly in its wings. It has a special line-like surface structure, and this is the reason why it shines blue or black. And the bug has no chemicals on the skin. It has here pillar-like structure, and the property of this structure is antibacterial. And now the CAMP can create directly these surfaces here with lasers on a lot of different materials. And we are doing this with some technologies. Here I'm going to present you two of it. First of all, the direct laser writing. Here we have a laser beam which is deflected by a galvanometer scanner and is brought to the surface of the sample. Here we receive a resolution from 5 up to 30 microns. And let me say it's a slower micro fabrication speed to the next technology I'm going to present you. And the energy distribution of the laser beam is here dot-like. Our main research area is the direct laser interference patterning. In this case, we have one laser beam coming into this DLIP optic. And in this optic, it is split into two sub-beams. And in this case, with a galvano scanner, it is deflected directly here on the surface of the sample, so that we can achieve a so-called interference pattern on the surface. Here we receive some feature sizes from 150 nanometers up to 30 microns, and it is much faster fabrication speed compared to the direct laser writing. So how many patterns can we generate with this DLIP experiments? In this case, we have here a line-like pattern on the surface, but there are thousands possible patterns possible. Here, it depends on the amount of sub-beams and on the type of polarization of these sub-beams. And here are some examples of surface structure like flower-likes or like a honeycomb. It depends on the application you would like to achieve. And how we can produce it. Here we have two scenarios. Scenario one means we have low pulse energy and a high repetition rate from the laser. Therefore, we need a significant amount of kilometers per second, and we receive significant heat accumulation, which is not good for our material because it will be destroyed with it. Scenario two means the laser has a high pulse energy and a moderate rep rate. Here we can achieve high throughput with large spot sizes, but unfortunately, the feature size resolution is pretty low. So our solution to make it better is the direct laser interference patterning. Here we have high pulse energy with moderate rep rates, and we are using the so-called interference patterning. Here we receive scanning speeds of some 100 meters per second. We will do this with a polygon scanner. We receive lower heat accumulation and, of course, higher resolution due to the interference pattern. And this technology we are integrating into LAMPAS. It is a multi-beam high-speed processing. Here it is shown the 6 sub-elements that we will develop during this project. First of all, we need the interference patterning for high resolution beam processing. The polygon scanner will bring the laser directly to the surface of the sample. And of course, we can't ablate or we can't generate a surface structure without any laser. That's the reason why we are developing an ultra-short pulse laser system. The inline monitoring system ensures the quality during the whole laser structuring process. So this I will present you in the next slides. And in the end, we have to integrate these 4 submodules into a whole new machine. And of course, we have to validate this machine with some samples in the end. In this project, we are 8 different project partners from all over Europe. So Trump is a huge laser developer. They will do the laser developing, and beam deflection system will be done by NextScan and by the Technical University where I belong to. The process monitoring system is done by NIT and also by the Technical University. The system integration, so the combination of all these sub-modules will be done by LASEA. And of course, the validation and demonstration is done by Bosch and BSH. And of course, let's say for organizing these events here, EPIC is doing the dissemination of LAMPAS. Now we come to this unique inline monitoring system for LAMPAS. In this case, we will monitor two process effects. First of all, the accumulated heat that we would like, that we don't want to have during the process. And of course, we would like to correlate this with the topography assessment of the patterned structure. And we are realizing this with a combination of a high-speed infrared camera, which is done by NIT. And what's also new, it is the second one that we are combining it. It is the fast Fourier transform system. So that's a unique measurement system for analyzing the topography of a periodic pattern. So what do we need for it? First of all, we need a laser pointer in a low power laser with a low laser power, periodic structured area, and of course a screen. We are using it here with a camera. So that means when the laser irradiation hits the area, the laser light is separated into like this into some clouds. We call this diffraction orders here. And depending on the quality of this laser structured areas, the intensity or the behavior of this diffraction pattern will change. Let me show it how it works in real life. Here are some examples of structured stainless steel. Here we have microscopy images of a good surface condition. Here you can clearly see the line-like pattern from the DLIP treatment, and there is no significant resolidified material on top of it. Down, there is a bad surface condition with a huge amount of resolidified material on top of the line-like structure. So in the end, the pattern was or is destroyed. We monitored this process with the infrared camera, and we can clearly see that there is a changing in the temperature depending on the surface quality. And of course, when we are doing this surface analyzation with the FFT system, we can also see that there is a change in the behavior of the diffraction orders. Here, when we have a good quality, like here we have on the left, on the top left side, we can see here the second plus minus second cloud, and this cloud we don't have here in the bad surface quality. So in the end, we have a powerful tool to differ good surface quality and bad surface quality. What are the objectives and benefits of LAMPAS? First of all, yes, we are going to develop a high power ultra short pulse laser system with up to 1.5 kilowatt of laser power. With this, we are achieving high throughputs up to 5 square meters per minute. The resolution is depending on the unique application. So with the monitoring system, we also achieve minimal workpiece heating, and of course, advanced surface functions on large areas. So the objectives of LAMPAS is, of course, development of a new generation of products. That means with different special applications. The performance improvement of these products is also pretty important. And what's for the industry also is quite good that we have here an accelerated product development. And what's pretty important for the European Union is that we are going to strengthen the global position of Europe in the world. For the ending of my presentation, I would like to present you some applications that we generated at the university. Here is the superhydrophobic properties. In the Petri dish, there is water and, of course, a laser structured aluminum sheet, and you can clearly see that the laser structured area doesn't get wet, so the water has no chance to cover it in total. That's the application number one. The second application is for colorful finishes. Here is a picture of my former colleague Stefan. Stefan was is a pretty nice guy, and we put this picture here on a polymer foil, which you can see in this video. And when you flip it, you can see that the colors are going to change, and this depends on the angle of view. And here you can also see how incredible fast this laser structuring process is with a galvano scanner. All right, we are now in the end. Thank you very much for your attention, and I think it's time for some questions. Francesca,
yes,
isn't it?
Yeah, correct. Thanks a lot, Nikolai, for the introduction of LAMPAS and also more focused on the monitoring system. So now that we are here, of course, there are a lot of possible topics that we can touch, because I know in this room now, and maybe in the future also who will watch this video, there are end users of the technology, especially from the steel industry, but also we have people that are willing to maybe implement their cameras in new devices and in new technologies. So let me pick the one that is a bit like the monitoring processing one. So I go for that. We basically heard now that MULTIPLE has its own technology, and you have, and of course LAMPAS has its own. We have laser-based technology. It's nice to say that we have the gas analyzers, but also your fast Fourier transform technology is also laser-based. So that's also nice to say. And then we have the camera side. So we will hear later from Rodrigo. But then we heard also from LAMPAS, from MULTIPLE, that we have also snapshot cameras for hyperspectral imaging. And basically the connection is, we know that our cameras from MULTIPLE can also monitor this kind of really inline, this kind of structuring processes. What is your opinion there? So we work in SWIR. So that's because the mid-IR, we know that Rodrigo is covering it. So why not talking about SWIR detection, and what is your thoughts? What are your thoughts, Nikolai, there?
Yeah, that sounds pretty good. So we are looking also for some new technologies in order to monitor this DLP process. So there's a quite huge range of monitoring possibilities that we don't know now, but I think there is a new one now.
Yeah, definitely. So there is room. Now we don't have the partners in the room doing this, but that's why we are here, to get to know each other. So that's a good opportunity. We have AMEN and IMEC in the consortium that are working on this. And so here in the room also we have some people working on this. So definitely we can reach out later and see what is that we can help you exactly with. And so that is what EPIC is doing as well. So
yeah, sounds good.
Yeah, very good. So now I guess I see a question from Thierry in the chat, but let's say this is probably answered by Rodrigo directly. And now, considering that this is Rodrigo time, let's leave the floor to him, and then we come back to him in case he's not really answering Thierry's question, okay? Rodrigo?
All right, thanks.
Thanks a lot, Nikolai, and we move on to Rodrigo. Thanks a lot. The floor is yours, Rodrigo.
Okay, I'll try to do my best, I promise.
You will, I know.
Okay, so I guess now you can see my screen.
Yes, and we hear you very well, so
okay.
We are ready to roll.
Okay, thank you, Francesca. So the presentation for today, my presentation is oriented to show some solutions that we have developed for quality assurance and process control in industrial metal processing applications, mainly. Just a brief introduction about our company. Okay, so we are New Infrared Technologies. We are a company that are based in Madrid, in Spain, and we develop and commercialize industrial solutions mainly for real-time process monitoring and smart control of industrial processes. We are a vertically integrated company. We cover all the steps from the detector concept to the final product, including the manufacturing of our own detectors, the production of industrial cameras, and the introduction of machine vision industrial interfaces, and also developing final solutions for integration into the production line, mainly for real-time and online process monitoring and process control. As I said, these solutions are based in our self-produced cameras. They have very specific, very noticeable and specific characteristics. They have detection in the mid-IR, covering the whole range from 1 to 5 microns, so they have a very broadband detection. They have high-speed capabilities, and very important, they can operate at room temperature without the need of being cooled. That's very important when you want to go into the production line, because our cameras don't need maintenance. Now we are also introducing thermal and cooled cameras, which will be sensitive in the long wavelength infrared band from 8 to 14 microns, but these are not based in our own technology, of course. We don't produce microbolometer sensors. So just a few lines about the solutions that are covered by our products in these specific applications in the industrial metal processing. We are mainly focused to provide solutions for quality assurance of laser-based processes, not exclusively laser, but very energetic processes like 3D printing with directed energy deposition processes or laser welding. We have combined laser welding with real-time machine learning processing, also for defect detection in real time, powder bed fusion or SLM processes, and hardening and surface structuring process monitoring and control, as is the case of LAMPAS. Also other processes like arc welding or wire arc additive manufacturing process monitoring and control. Spectroscopy, it has been one of the topics in multiple in the previous presentations. We have customers that have developed dual comb spectrometers based in our high-speed cameras, and some other applications that you can see on the right. We have a strong collaboration with the industry through H2020 projects. Of course, one of them is LAMPAS, but also others like Integrade or Custodian. Our aim is to put our technology in production line in many industries like the automotive, aerospace, steel, among others, for example. These are some of the products and solutions that we offer into the market. Of course, they are targeted to integrators, solution developers, and end users. You can clearly see that we have some on the upper left part, some basic detectors like line detectors or single element detectors. In the case of the linear arrays, we have a few customers in the steel industry that are using our sensors for detection of defects or contaminants in the steel rods right after production. That's one of the samples of our products. But I think our very different products are based in the imaging sensors. So we have right now our state-of-the-art is a 128 by 128 pixel detector that we have integrated into a camera called Tachyon 16K that allows to acquire up to 4,000 frames per second in uncooled operation. As I said, this is very important to introduce the camera into production line to monitor the process, as we have seen from Nikolai, the presentation from Nikolai before. We also have some solutions that are integrated directly in the machine, and they can do process control, like for example, Clamir. I will show some examples now, or monitoring of the melt pool width, for example, that can be linked directly to the quality of the process. And now, as I mentioned before, we are introducing a new line of thermal cameras called the LIR 320. This is a very compact camera, a thermal camera with characteristics or performance characteristics totally different than the other cameras, but very useful because it's a very compact system that can be put easily into the production machine to monitor temperatures for predictive maintenance and those kind of applications. Just one example of these solutions that I mentioned before is Clamir. Clamir is an embedded system. We have integrated the infrared camera with a board to do image processing that extracts some features of the melt pool. In this case, this system is made for laser directed energy deposition processes, laser metal deposition as it's known, in which a powder is deposited or is passing, ejected through the laser, and then a material is deposited to build a part. Okay, so as I said, we have Clamir that combines the infrared camera, the image processing, and the control electronics, and this is connected directly to a laser, and it's capable to close the loop and control the laser power during the complete process. In this case, we enhance the quality and the repeatability of the process. It's a system that is very easy to integrate mechanically and very quick to configure. It's important, and it allows retrofit. meaning that it can be installed in machines that have already been built for this application. As I said, the main applications of this camera is the LMD and laser cladding, including the high-speed laser cladding, ELA. And where on the left you can see the system installed on the TRUMPF laser optics. I will now give some more examples. So in the case of metal processing with this specific process, the laser metal deposition, you can see some examples of what Chlamyr is capable to do. In this process, here you can see that, let me see where the, here you can see what can happen when you build one part without process control, without taking care of the laser power. It can happen that the part overheats and the process needs to be stopped because in the end the part produces doesn't comply with the quality asked to the system. This happens because of an excess of power, and what Chlamyr does is precisely to control that laser power and enhance the production, the productivity, because then the part can be produced without interruption. This reduces the rate of defective parts, material use, and energy done in a controlled process. And in this case, the process is optimized, and also the productivity. Here you can see an example of a massive metal part built with Chlamyr process control without interruption, the whole process. And here you can see what Chlamyr is doing. Actually, it's monitoring the melt pool in real time, and with this monitoring, it determines it measures the melt pool width and uses this reference value in order to control the laser power. Here you can see the blue line, how the laser power is being controlled in real time. This you can see here in this video. You can see exactly what Chlamyr is doing. You can see here that a triangular shape tube is being built using this technique, and without control, you can see that there is an excess of power up here, and there is accumulation of material on the corners. And actually, you can see that the quality of the finished part is very different, very rough, compared to a part built with process control with Chlamyr. Okay, I can show. See now. Here you can see in the video. You can see. Hopefully, you can see how Chlamyr is acting on the laser power in order to to produce the part continuously without defects. Okay, here you can see on the edges that the part doesn't have good quality, but with Chlamyr, the quality is very high quality is achieved. Also, the same kind of process, but in order to, another process is called laser cladding. Another laser-directed energy deposition process is called laser cladding. This is a continuous process that is used to apply a metal layer on substrates in order to solve possible worn-outs or prevent corrosion, to apply another metal layer in order to change the properties of the original, of the base material. This is done also by depositing the powder with the laser. And in the case of, and in this case, it can happen that an excess of power can damage permanently the substrate material. Here we can see it on the right side here clearly. In the case of Chlamyr, what it does is control the laser power in order to avoid this and allow continuous processing without interruption and without damaging the base material. So in the case of Chlamyr, we have process monitoring and process control. Then we have another system called i3MS, which allows only process monitoring for metal 3D printing or for laser welding. It's a system that can detect if there is a variation, a large variation in the melt pool width, which is linked to the quality of the process at the end. So the system can detect if there are these variations and give an indication of the quality to the user. Okay, and then we have the high-speed camera. This is the camera that is being used in LAMpAS project. It's a camera, as I said, that can achieve a maximum frame rate of 4,000 frames per second, but it allows also to go at higher speeds. One of the advantages of our technology is also that as it has detection between 1 and 5 microns, it allows coaxial or on-axis observation through the laser optics. For laser processes, this is actually very, very important. And actually, you can see here a video of a MULTIPLE, the MULTIPLE variation in a PBF process. Here we have on-axis observation. You can see that the MULTIPLE is always in the center of the image. With this data, also it's possible to calculate the cooling rate based in this thermal information, which can be used to determine if there have been defects during the deposition. Okay. This was my presentation. I just wanted to give you the attendants just an overview of our solutions that can be used for process monitoring and for process control with, in the case of steel or metal processing applications.
Thanks a lot, Rodrigo. That was really covering a lot of applications. So, of course, additive manufacturing is something that we know that NIT is really strongly interested in and devoted to. Also, laser beam welding, of course, that's your specialties. Now, I would go back to first to see if Thierry is happy, because if Thierry is not happy, we cannot go on. So he was asking you to exactly define what are the exactly measured by the camera and how it is implemented in process control. Correct, Thierry? Do you want to add something now that you saw the talk?
Yes, it's perfectly clear. So it was, yes, I didn't notice that Rodrigo was to speak after, but yes, he answered the question basically, and I learned a lot of things. Thank you.
Thanks a lot, Thierry. So then it was worth to wait. Then I have to say, let's say there is one point that we hear often. So a question a bit more to Rodrigo. I guess this is not maybe the issue now for LAMPAS, but is in general what we hear more often, that basically some applications more towards additive manufacturing would like to have more frame per second. Is it something that is actually hassling you? Are you thinking about it? What is the approach of NIT on this?
In the case of, I think in the case of Clamir, we are operating at 1 kilohertz and we are fine with it. It works really well. And as I said, it's compatible with high-speed laser cladding process, even at 1 kilohertz. For some more demanding applications like PBF and the sample that I showed in the last slide, it's necessary to go at higher speed. In our case, with the camera at full frame rate, we can achieve 4,000 frames per second in a snapshot acquisition, meaning that we can acquire all the pixels at the same time, and this is also an advantage. But in case that it's needed to go faster, we can window a little bit the acquisition. I mean, we can make it narrow, the acquisition window, and that improves the speed. I would say that infrared, mid-IR, high speed, uncooled, those are the characteristics of our cameras. And at the moment, there are no other technologies that can achieve that. Nevertheless, we always have it in mind for the future developments that we have a reference in the market of high speed. So even if we go to higher resolutions in the next generations, we will have to keep the high speed capabilities because that means that we will open our sensors to other applications and also give support to the existing customers. This is something that we have in mind, but at the moment, with this camera in 32 by 32, we can achieve 10 kilohertz. 32 by 32 means that, I mean, it's maybe not high resolution. I mean, it's probably a small resolution.
You have to trade off.
But yeah, but when you look at data at 10 kilohertz, this is like an HD signal, and it's a lot of data that you need to analyze in real time, because the idea is also to have a real-time process monitoring and process control. Exactly. And in the end, there is a computing system that needs to get all that data and analyze it in real time. So that's also a challenge.
A challenge, yeah, of course. So that is also what is needed by companies like yours, or also like from MULTIPLE as well, if we want to really also address these kind of processes, that you have always to see what is the trade-off and where is the position where we can take off maybe some characteristics to increase the other one, but still we want to be inline monitoring. And so also we don't want to cool them. So there are a lot of things that have to be balanced, and maybe speaking not on a custom-made level, but maybe on a category level, you can already address the needs of some applications in a broader way, and then go deeper into the demands of the customer. So that's definitely good flexibility from your side. So very good. Thanks a lot, Rodrigo. So now I would say, if there are no questions more, I have to wrap up a bit and maybe say what is the future of these two projects, because EPIC is here also not only to let you know about them and talk to the actors of this project, but is also there to exploit them. So we want them to be successful. And so, as you heard from the beginning, we expect from MULTIPLE now, especially for the monitoring process systems, already the first results from Ignazio in September. So it's really, we are really close to get some hints on how this is working now, the monitoring system there. So we will keep in touch. We will make an announcement when we are allowed to announce the results. So I just say stay tuned there, because that is what we want to show. And then we will have another 1.5 years to think about how to apply this, how to optimize it, and also maybe bring it towards other companies that are sitting here or at the moment, or they will listen to this and watch this webinar later. So we are there, we are coming. So please pay attention to our press releases and announcements. And from the LAMPAS side, we are always also there looking for results, because we want to extract the most possible. And the sooner as we have also the validation of this surface structuring, we are looking as well for customers, so for anyway, first end users that would like to test their surfaces, so that we can basically, as a service, structure them and then see if the qualities or the properties that we are giving to you are actually satisfying your demands. So the idea is now in the upcoming months to also validate. So we are in the validation process there as well. So once we have the certainty that our machine can do something for you, we will also announce this, and you are very welcome to just reach out to us. And I mean, in case you didn't check earlier, this is still my email address, so you can see it here, here below. So anything that is interesting for you that you heard today, or that you know that will be interesting for you very soon when we have validated all the technologies, because as we said, it's really a matter of months, please feel free to reach out to me, and we can put you in contact with all the partners also for tailored services, but also for the entire project aims to bring you really close to what these two projects are doing. And so now I would say, let's close this public event now, and I would say bye-bye to everybody, and let's keep in touch, because there are a lot of developments going on, and you will hear from us very soon. Bye-bye.